Hi everyone! In today's video we are going to discuss how to prepare alkynes or triple bonds. There's a couple different ways you can do this. The first method involves using something called a geminal dihalide, and the second method involves using something called a vicinal dihalide. So let's start by reviewing how to make a double bond, and then we'll kind of add on to that and show how to make a triple bond. All right, so let's just do a little bit of review. So recall that when you're making an alkene, you need a good leaving group and you need protons on a beta carbon. You also need a strong base. Additionally, this is going to be an elimination reaction. So remember, elimination reactions are favored at higher temperatures. So we'll just add a little delta symbol there to indicate that we're heating the reaction. All right, so this is an E2 process. Remember, E1 is pretty rare. You would need a tertiary carbon bonded to a leaving group. And then you'd also probably end up with some SN1 products as well. Okay, so we have our strong base. Let's figure out where our beta protons are. So remember, the alpha carbon is the one bonded to the leaving group. And then the beta carbons are the carbons next to that alpha carbon. So we do have two beta carbons. But the one on the left, notice that it doesn't have any protons bonded to it. So we won't get any elimination at that position. However, the other beta carbon is bonded to 3 hydrogens. So the base can come in, grab one of those hydrogens, and remember it's the lone pair that's grabbing onto the hydrogen. Then the electrons are left behind to form a double bond, and then the leaving group is kicked out. All right, so then we end up with a double bond. So that's our alkene. And we would actually call that a terminal alkene because it's on the very end of the molecule. All right, so now what about alkynes? How can we make a triple bond? Well, we're just going to perform the reaction we did above twice. So that means we need 2 leaving groups. So let's start with a similar molecule, but this time we'll have 2 leaving groups bonded to that alpha carbon. Okay. Now this is what we call a geminal dihalide. So dihalide means that we have 2 halogen atoms. And then geminal means that they're bonded to the same carbon. So I kind of like to think about it like the astrology sign, Gemini, which represents twins, right? So geminal dihalide, we've got 2 leaving groups bonded to the same carbon. All right, so then we're going to use a strong base again, and that's going to take one of the hydrogens bonded to the beta carbon. So pretty much the same as what we did above. And we're only going to kick out one of the leaving groups. So we end up with this intermediate where we do have our double bond, but one of the bromines is still left over. So we can perform this elimination reaction again. So we still have 2 hydrogens bonded on the end there. So our base can come in, grab one of those protons, and they'll leave behind another pi bond. And then the second leaving group will leave. And then we get our triple bond. And notice that I drew the triple bond going straight up. And that's because when you have a triple bond, the bond angles are at 180 degrees. So the geometry is linear. So just remember there's 180 degrees around the triple bond. Now the alkene above, we can have an angle there because that will form a 120 degree angle. But alkynes are linear. All right, so in this case, we actually don't stop at the alkyne, at least not right here. There's actually a couple more steps in this mechanism. Now, we do have one last hydrogen on the end there, and we are using a strong base. And it's not as if we just have two base molecules. We actually have multiple base molecules, so we have an excess of base. So the excess base is strong enough to take that hydrogen that's on the end. So it actually comes in, grabs that hydrogen, and then the shared electrons are left behind as a lone pair. So we end up with an ion, an acetylide ion, I believe it's called. Let me double check. There's a name, a very particular name for it, and I keep mixing it up with acetylide. Oh, it's an alkynide ion because there's an alkyl group attached. Alkynide. I have trouble remembering that name. All right, alkynide ion. All right, so in the next step, we probably want to reprotonate that ion so that we have our triple bond without the negative charge. So what we're going to do is add a weak acid. And that can just be as simple as using water. All right, so that lone pair on the alkynide ion is going to come in. It's going to grab a hydrogen from water. And then, of course, electrons will be left behind on the oxygen. And we end up forming our final product, the alkyne. All right. So that might seem kind of strange that we don't just stop at the first alkyne. We actually have this whole deprotonation process after that, and then we reprotonate the ion in the last step. However, that intermediate, the alkynide ion, is pretty stable because recall in our last lecture we talked about how this ion or the carbon that is negatively charged is sp hybridized. And that means that lone pair of electrons is really close to the nucleus. And that's very stabilizing. So this is a very stable intermediate. So forming that intermediate is not a problem energetically. All right, so now let's talk about the other way that we can form alkynes, and that's by using something called a vicinal dihalide. All right, so in this method, we're still going to start with something that has two leaving groups, but instead of being bonded to the same carbon, they'll actually be bonded to separate carbons or adjacent carbons. So again, a vicinal dihalide tells us that we have two halogens, but the vicinal part tells us that they're bonded to adjacent carbons. However, the process is still the same. The base comes in, it grabs a proton, a leaving group leaves, and then a second molecule of the base comes in, grabs another hydrogen, and the second leaving group leaves. So we do end up with the same product. So in step 1, we use our base, we get our alkene, and then we get our alkyne. And then in step 2, we still have to add a weak acid to reprotonate the alkynide ion. So very similar process, but the leaving groups are on separate carbons. All right, so let's draw our same product that we saw before. Okay, so I mentioned that we do need a very strong base in order to perform this reaction. The most commonly used base is sodium amide, or amide, however you want to pronounce it. I've heard it both ways. Now, you might be thinking, well, what about hydroxide? Sodium hydroxide is a super strong base, right? That's usually what we use when we need a strong base. But unfortunately, the hydroxide ion is too weak to deprotonate the acetylene proton, or the alkyne proton. So I'll just put a little asterisk there, something to remember. Okay, so now that we know how to prepare alkynes, in the next video, we're going to start getting into the different reactions and mechanisms that we can perform using triple bonds. And the reason that we're interested in these reactions is eventually we're going to talk about synthesis problems. So how do we get from one functional group to another? Or what's the easiest way to form a desired product from chemicals and reagents that we have handy in the lab? So we're going to dive into all of that next time. So I will see you then.